make some demonstration of how to set up a GaN nitride HEMT device. Okay, so the sample we are going to demonstrate is a very simple case, just like figure shows. This is a simple aluminum GaN nitride HEMT device, and with aluminum nitride barrier and aluminum GaN nitride 20 nanometer barrier. And there's a 2 nanometer GaN nitride cap there. And with the surface preservation, and so we have a silicon nitride on top, and there's a drain and the source and the contact. Okay, and in the bottom there's a carbon dope. And for this kind of deep trap doping, we will use the deep level trap as an example. Okay. So this is the structure we are going to demo today. All right. So for the 2D DDCC, when you open the interface, the first step is that since we are going to make this HEMT structure, it's just like a material growth, and so we will need to set up the layer. And the layer we are going to work is the first is the carbon dope GaN nitride and the GaN nitride channel, aluminum nitride, aluminum GaN nitride, and the CAM layer. So when setting the material, we can set up the layer material range first. Okay, and before we start this, let's set up the total region. So I didn't demonstrate how large of the lateral size, but for example, that if the total length is if we set up is like 2.3 micron, so we can add there, and the total layer length here that we could be okay 2.3 micron, 2.2 micron or 2.2 micron. Okay, and we can put this first, and we add the first layer. The first layer we are going to add is 1.8 micrometer GaN nitride. So we can set up 1.8 micrometer, and this material is aluminum GaN nitride. So we say composition is 0, and let's say let's set up the doping. The doping is 0. We don't set up doping first. Okay, and we apply. This is the first aluminum GaN nitride. Then we can set up a 0.2 channel GaN nitride channel. And this is a GaN nitride composition 0. And for this second layer, then we need to add aluminum nitride layer. So aluminum nitride layer, let's set up the composition to be 1.0. And the total thickness here, okay, is 1 nanometer. So we can say that we set up 1 micrometer, 1 nanometer. So it's 0.01. Okay, and I think this is N-type. Okay, and you can say that if there's an intrinsic background doping, 1E0E16. Okay, apply. It's a very thin layer here, and then there's a aluminum GaN nitride layer, which is 20 nanometer, so it's 0.02 micrometer, and the composition, as we believe, is 0.25. So let's say 0.25. Okay, and let's say it's N-type apply. So that's the force. And actually, we can adjust everything later. So we can just GaN nitride cap there. So it's 0.02. Okay. And okay. So it's 0.02. And then we can say that let's put the composition to be 0. So it's GaN nitride candidate. It's like here. Okay. And let's apply it's 2 nanometer. Then let's say there's a silicon nitride there. Okay. And let's find in the material database if we can find the silicon nitride. Okay. So let's say there's a silicon nitride here. Okay. And the thickness is 0.02. That's for example. And no doping. Let's say 1. Okay, let's apply. So that's the setting of agitation. And then we want to etch down for drain and source. So then we need to set up an etched layer. So let's set up a empty section. So we can etch down the layer here and here. So how to etch down? Let's set up empty section. And we can say it's a rectangular, okay, and it's a single layer. Actually, you can set up a period layer, but for my HEMT, we may not need so many periodic layer. So the first region we are going to etch down is in this region. So the total thickness, I believe, is that we need to etch to 2 micrometer. So let's set up the electrode, this position. Let's say this is F1 and F2, the thickness is 2.0 micrometer. And then the total layer thickness, including the silicon nitride, is around 40. So we can set up F3, okay, it's 0.25. And the total thickness is 2.23. And you apply 1, you can say that you can see that here is etched. So we can etch another position. Let's say it's like 1.95. It's for the drain contact. So we say 1.95. Then the final end is of course 2.2. Okay, and we can apply. Then this location is etched down. Okay, then we need to etch is here, the gate region. Okay, and we can set up the gate region etching down. Okay, let's say, let's say the etching gate region here. Okay, so when we etch down, the third one is in the under the center. So let's say F1 is 0.085, and then the gate length is 100 nanometer. So the etching that's going to etch is from 2.023 to 2.23, and that's we just etch down the silicon nitride layer. And okay, and the F3 that we can say the F3 the etching position is the right hand side, so 0.95. Okay, and 2.23. So this here, right? Okay. So if you look at this, you can find that we just make the etching down of the device to be like a HEMT structure, just like the etching of the AP layer. Then we can put the electrode. Okay, let's set up the electrode. Electrolyte, the first contact for the electrode, okay, is the contact of top layer. Again, contact of top layer, there are two kinds of contact. One is linear contact and one is area contact. Linear contact, that means you put a contact from here to here and you will put a contact below. So we can, for example, we can set up a linear contact. Let's add 1, start from 0 to 0.259. And the contact type is source. Okay, contact is on the top. And we can set up this. This is the first contact is here. Then we can set up second contact. Okay, it's 1.951. And then it's 2.2. It's top. And it's drain. Okay, and let's apply here. Okay, the final is that you can set up a gate contact. So for the gate contact, I can give you another way to set up is that since we need to have a contact that's close to this edge and the button, we can give you another example of setting the drain contact is that we can use the area contact. And so here, and we can add area contact. And area contact, currently the shape is rectangular. In the future, we'll add one more feature. So the area contact, we can set up the F1 and F4. So F1 is 0.849 and F2 is 0.951. So we need to enclose the surface of the sidewall. Okay, and the 0.3 is 2.05, and the final point is 2.021. Okay, so if you apply the contact here, and if you look at the contact here, it's just like you put up a gate contact surrounding the material region. Okay, so this is the gate area contact. Okay, after finish this contact setting, all right. If we don't consider the thermal effect, we can end up here. But if we want to consider about thermal effect, we need to set up the thermal. Okay, the thermal in our experience, we already test some example, so we put some thermal effect. Okay, so let's say if we put another linear contact region, and this is the thermal contact, and this is only 2D simulation, so most heat was dissipated through the bottom. So we can add another thermal that the contact region is on the bottom, and it's from 0 to 2.2, and the contact type is the thermal and the heat diffusive. We cannot put the heat fixed because there is also some buffer layer on the bottom, but we don't simulate it, so we need to use diffusive boundary condition in the bottom, and we can apply here. Okay, later I will tell you how to set up thermal, but right now thermal is like this. Okay, close. So this is the setting of the mesh for the HEMT device structure. Then after that, we have some more region to set up. Okay, the more region we are going to set up is the region we mentioned here is the drain and the source heavily doped region, because in this region usually we use the titanium nitride to put on top of GaN nitride or aluminum GaN nitride at near. So we can say this region is like ohmic contact region. So we need to put a heavily doped region here. Okay, we need to put heavy dope. So let's set up a region that's believed to be like a highly doped titanium nitride material on the contact. So we can set up the local range, and the local range we can add a first range. Okay, the first range we are going to add. Okay, let's say assign material first. Okay, so that's all this region was set up. So we can add local range. Okay, the local range we are going to set up is a rectangular, a single layer material, and let's say the F1. Okay, the F1 is 0, and that's the region. Let's say the region here. So the F1 is 0, and F2 is 1.9. Okay, we only set a very small region. This is the example we are going to show you. And the F3, okay, F3 is 0.25. Okay, that's on the right hand side. 0.225, and then is the region is 2.0. Okay, we apply here, so you can say there's a heavily doped region here. Okay, and then we can add one more layer. Okay, here we need to add one more layer. Okay, I choose the raw material, so I need to choose back to aluminum gallium nitride, and later we will fix another arrow on the right hand side. But anyway, this F1 is 1.95, and this is 2.2, and we can apply. It's here. Okay, it's aluminum gallium nitride, and that should be a heavy dope there. Okay, so finally we set up the whole AP structure layer, and if you refresh, we can set up the material layer. Yes to all. Okay, so we have two local range, and you can find I set up the material wrong in the local range, so we change to aluminum gallium nitride back, and it's happened though material. Okay, so the total material we are going to do, okay, it's like this. And since this is a titanium nitride, let's say it's a heavily doped. Okay, we can change this value by fitting the contact resistance. Here, I just give an example of our working sample, and we'll give you the second file in the later, so you can take it as example. So this is a aluminum gallium nitride region. Then it's like a heavily doped there, heavy doped material right here. Okay, and then this is a setting, and for setting, we can check about the mobility region. So this is a spontaneous polarization, and this is a polar charge. And then in the heavily doped region, the mobility can be set up to be smaller. For example, this example is fitting some experimental parameters and with a very large contact resistance. So in the contact region, we just set up electromobility to be small. But since we don't simulate hole, so it's not important if you need to change the default hole mobility or not. Okay, and then this is the whole structure we are going to model. Okay, this is the whole structure we are going to model. All right. So then there's a channel layer, and this is the mobility setting. Okay, and then let's hope That's the setting of the material layer. Okay, so this is the basic setting, and then we can set up a mesh. We can set up a mesh. For first test, you can use the closed mesh setting, and you can generate the mesh. Okay, so the program will generate a mesh for you, and you can find the mesh density in the X position, and then in the Y position, this is the mesh density. Okay, okay, all right. Then if you want to check if the mesh is good or not, okay, you can save the project first. File save as the project, and then we can start to do some mesh. Okay. And then there is some example. I will show the result section that we already run, because running the HEMT simulation will take some time. So we have some example here, but here we can put up the second file, and we can say this is a project HEMT. All right. So let's check the mesh. We can make a real mesh, and then we can check the mesh quality. Let's say show figure, and we can plot the mesh. Okay, so this is the example of mesh. You can find that this in this case, the mesh is really bad. Okay, and there is a discontinuity here. So we can tune the mesh. Okay, in the S direction, it's better to have a good mesh. So let's say the smallest required DS, or we can say, all right, I want it to be 2E minus 4. Okay, and we can set up this. Control C and Control V. And then we can refresh. Okay, then we can set up the tune mesh in the X direction, and we can make the mesh again. Let's plot the mesh. Okay, then you can find the mesh becomes more smooth, and this the size is smoothly changed, not just suddenly changed. So let's set up this closed mesh first, since we are just going to demo. But even it's closed mesh, you can find the mesh density here is quite high. And actually there's a large electric field here, so later we may need to come back to tune the mesh. In this occasion, use the manual mesh. Okay, so this is the mesh setting. Then in the GaN ITRI, the most important things that you need to be careful is about the surface. Okay, the surface potential contact setting. So as you can find, this is aluminum nitride, and this is a GaN nitride, and this is a sapphire. So in the alumina, okay, in the silicon nitride and the GaN nitride interface, okay, sapphire and silicon nitride interface, we know that there's a negative polarization charge here, but there is also a high density of trap. Okay, since there is a negative polarization charge, they will trap a lot of holes to pin the Fermi level. Oh, okay, they will pin the Fermi level around the middle gap. Okay, so let's say if the middle gap, oh, okay, is like something like, oh, if we say there's a middle gap trapping, then we can say there's a trap, and a trap like at a 2.0. You can change the value by fitting. It's not necessary to be this. So you can say there's a 2.0 trap. Okay, and then there's a large polarization charge difference. So there's a huge density of whole trap. And for example, if you look at the polarization charge in the GaN nitride material, there is a large density of polarization difference. For example, this is GaN nitride, and this is sulfide, and silicon nitride. So there is a polarization charge difference is 2.15 to 0. Okay, so there's a trap here, but this polarization difference will be compensated by the surface trap. So there are few tricks to do. First is that you can set up sulfide, silicon nitride to be the same polarization of GaN nitride. So you can set up 1.25 E13 here. Okay, so if you set up the value here, okay, then the polarization was been tuned by you. So there is no polarization. That means that you remove this sigma, then the trap density you can set up is smaller. So if you don't change this, then you can use the trap function. Okay, let's refresh again. You can set up a trap region. Okay, there's a trap region. You click, and you can set up a trap density in the GaN nitride silicon nitride interface. Let's say this 2 nanometer range. Okay, you can set a very large trap density. Okay, the trap density could be trapping the holes. Okay, and trapping the electron. So it's like multi-level traps. It's like multi-level traps. Okay. So what you can do here is using a trap to pin the Fermi level. That's one way that you could do. All right. And since the polarization charge density is around 2E19, it's around 2.1 times E13. So the GaN nitride layer is 2 nanometer. So it's 2.0 times 10 to minus 7. So let's say the charge density is around, okay, you can compare this, it's around 10 to 20. Cn minus 3. So this is a very high density, trap. Okay, so if you want to compensate this one, okay, you can say that it's a fixed polarization charge, and you want to compensate that value. Okay, you can say I want to compensate that value. All right. So what we can do is that what we say, we can set up a trap here. Okay, like this, and put the electron trap, and we can say that there's a polarization charge is the same as here. Okay, let's say refresh. All right. And you can always check up the output file, and here, so you can find the polarization charge here is modified as well. And this is the polarization. Okay. Then we can set up this electron charge. Since this is a surface potential, we can set up an electron surface charge here. And let's say it's like 1E19. Trap level is 2.0. And tau and tau p. Tau and tau p, we can say that it's like a surface trap. So it's a long lifetime trap. So you can say it's like 1e minus 5, 1e minus 5. Okay, so this is a service trap setting. And since there's some electron, so we can put some fixed charge here. Okay, and we can say that there's some electron charge might happen here. So let's set up 5.2. This trapping density, so that it can be trapped by the surface. Okay. Then this is a setting. Then finally is the setting of the carbon dome region. Carbon dome region, you can set up the carbon doping in here. That's the first layer. Okay. And if we say it's a deep level trap, let's say 1.1E17 electron trap. Trap level 2.5. Okay. And the trap lifetime is to be longer since it might be a long lifetime trap. Okay, so that's the setting of trap. So that's the setting of trap. Finally is the transistor setting. And the GaN nitride usually will use the field-dependent mobility. And there's an example of the field-dependent mobility for GaN nitride we provide. Okay, this is the field-dependent mobility. It actually is just like a too simple file. And this actually the size of this mesh is different, and you can check that you can find that the size here 131 to 132. There's a large difference in the spacing. So there's a separate point 131 here. You need to put up here, and there's another. It's the channel region setting. So we know that the channel. Okay. The channel in the material is from here to here. So we can set up the channel. The channel we are going to set, okay, is 2.499 E minus 5. That's the starting point, 0.25 micron, and to 1.95 E minus 4, 1.5. If you want to make it safe, you can put it a little bit longer. And why the channel is including the aluminum nitride layer, so it's 2.0001 E minus 4 to the 20 nanometer channel, so 1.8 E minus 4. Okay, so that's the channel layer. So you can use the field-dependent mobility in this channel layer. So this is a transistor setting. So before that, then ideally we can do some simulation to check out the structure if we are going to match is right or wrong. So let's save the file, save the project, and run a testing case. So before running this, we need to set up the contact. So let's say that there's something contact need to do. First is that this kind of material, we need to use the affinity. So the default is already chosen affinity. Then we need to set up the circuit barrier. So we need to use the circuit barrier for the material. And we can say that the circuit barrier can use metal wall function, and this is 6.1 EV. It's a circuit barrier. Okay. Then what else we need to say? We can run the 0 volt first if we don't apply any BIOS. So if everything is right, the left thing we need to set up is the thermal setting. The thermal setting that here is the thermal, and the thermal part, okay, we need to know the materials thermal dissipation coefficient here. Okay, there's some arguable value is the aluminum gallium nitride because the program still uses the linear interpolation. So we can choose it to be a smaller since aluminum gallium nitride is not linear interpolation. So we can set up a smaller value here. Okay, and here is the aluminum gallium nitride. So I believe it should be 0.0. That's because it's not refreshed. Originally we set up the silicon nitride. So then we want to solve the thermal problem. We want to solve iterative with Poisson-Drake diffusion, and we use the association boundary, and we assume that the association boundary distance is 5 E minus 4, like 5 micron. But usually this is testing value to test the temperature, and we use the temperature-dependent mobility as the model. And the coefficient we are going to set up is 300 minus 1.5 is P2. P2 is A, and the T0 is P1, and the P3 is 0.4. Okay, so this is the thermal part. This is thermal part. Okay, so this is the final setting, and we only set up is the thermal coefficient in this part. And then there's some field-dependent mobility coefficient and tau and tau p. We don't apply it here. Okay, so we don't use the local mu chart will be changed. Okay, and we don't use tau and p. Okay, right. Okay, so let's run the first test. Let's run. Okay, everything is fine. We will run the 0 voltage case to check if we have made any mistake. Okay, if you are watching the video, you after we simulate the result, okay, we can start to check out the data. Okay, so this is a directory we run, and we run the 0 voltage. Okay, and we can plot the EC. So as you can see, that there's a EC, and this is a 2D plot. Okay, and if you check about, this is carbon dot region, so the potential is a little bit pushed up. Then we'll check about this. Okay, you can find this is the channel region, and this is the source and drain, and under the gate region. Okay, you can make it larger and larger. Okay, so this is a 2D node-based data, and you can plot the region under the gate. Okay, the gate region maybe is E minus 5, 9E minus 5 centimeter, so it's around 0.95 micrometer. So you can plot the EC. Okay, and put the hold down. You can plot EB and EFN. Okay, and this is the surface top. Okay, so we can magnify here. So this is a argon barrier. Okay, so we can also plot the surface potential along the silicon nitride layer. So we can plot 5E minus 5, and we plot EC. Okay, this is the surface potential area, and we can plot the EB, and also we can plot EFN. Okay, you can see the EFN at the surface of in the location of 4.95. And you can look at the raw data. So you can get EC, EV, EF, and EFP. So you can simply choose them, copy them, and copy them to Excel to plot whatever kind of plot you like. Okay, so this is a 2D node-based data. Also, you can check about the element base. Element base means the electric field. Okay, so you can plot the EY field or EY field along this position. Okay, so you will find out the most position close to EY, and you can find the electric field here. Okay, and this is the electric field. So the beta is to plot about the log. So maybe the log profile would be better. This is not the log profile. Log Y, maybe, I guess. Okay, so this is the electric field profile, EY field. Okay, EY field along the channel. So you can find this discontinuous here and here. So this is the EY field, including the heterojunction. And of course, you can plot the pure EY. Let's remove the effect of heterojunction. So it could be more reasonable in some sense. Okay. All right, so this is the electric field caused by polarization field. So this is the EY, and actually there's a very strong field at aluminum nitride barrier. Okay, so except this, you have a lot of things to plot like mu and pure EY, ES, GN, JLS, JY, JPS, JPY. But before that, I must say that because we haven't applied bias yet, so we cannot get the current data. So we can check the parameters. Okay, so we can check the band gap. Okay, and let's say it's a 2D plot. So we can check the material band gap for 2D. Okay, so we can check the band gap difference here. All right, this is okay here. All right, so look at here. So this is a aluminum nitride layer. Of course, this is just a gradient, so you see some color discontinuous, but it's fine. So also we can plot the band gap here. Okay, so this is the second nitride spec. You can check about material parameters such as mobility or tau and tau B or generation or anything you want to check if the setting is right or wrong. So after this, we can stop and we can start to run some BIOS condition. So for example, if we can run at the 10 volt, and we say the VG start from minus 4.5 to 0 to 0. Okay, so okay, sorry. So we can load. We can load the demo here. Okay, right. So we can say that use the metal work function, and then we can set a bias from 10 to 10, minus 4 to 0, and VG step equal to 0.5. And you can simply click run. Okay, yes, and run, Okay, I click OK. Then the program will start to run. Okay, just like what you see, it will start to run the program. Okay, you can see the output. All right. So you can wait for a few minutes so you can get a result. Okay. And so I did run some case just before this video start. So we can look at the profile. So after we run that, we can say we have VD equal to 10 volt and VG equal to minus 4.3, so let's say 3 volts. So this is under bias condition. So you can plot the EC. Okay, so the EC profile of the HEMT of 2D structure can be plotted by this. Okay, so this is the potential profile here. And you apply the 10 volt and you check this and you get a surface potential. Okay, so you can plot the surface potential along y direction. Let's say 1.99 E minus 4. And you can plot EC along the y direction. And you can find that you apply the 10 volt and this position is just around the gate. And there's a potential bending here, and this is the change of the potential. And also you can plot the 2D element data, and you can plot the pure ES field. And plot this, you get two electric field. One is here, and one is here, and one is here. So you can get the electric field profile for VD equal to 10. So you see this, there's a huge electric field, like 1E minus 6 here. And there's a doping induced potential profile, but this region is small, so it won't cause the breakdown. And also there's another electric field in this event due to the doping profile. So if we check about the EC again, okay, this field is coming from this one and heavily doped region. There is a large potential change in along this direction. Okay, so you can look at this, and also you can check about the current. Okay, just said about the current. The current you can plot. What you can plot is the JNS and JNY, and of course the observed value of JNS. So in the 2D profile, you can plot the current. And usually current is you need to plot the log scale. But anyway, we can look at the current profile here. So if we plot the log scale, and we know the current density largest is 1E8. So let's say the upper bound is 2.5E8, and then the lower bound is 2.0E4. And after setting the upper and lower bound of the log scale, okay, so we can see this is the log scale plot. Okay, so you can say that the current injection is flowing down to here and then flows through the right hand side. Okay, and then flow. So after you apply minus 3 volt, you decrease there's a depletion in the current density. Okay, there's a depletion of current density. So there's a still field current, then the current flow back to here. This is a JNS. Okay, and you can plot the JNY. JNY, you also need to plot the log scale. And we know the upper bound is 4E7, lower bound like 4E, like I say, 4E3. Okay, so we can check the upper bound and the lower bound. And then we plot the profile. Okay, so You can find this is the current. Of course, this is GNY. So this current is flowing in this direction, so you didn't see GNY. And then you see the current flowing down. Then you see the current flowing up and then going this, and there's a little bit current flowing in this direction. So this is the current plot. And also you can check about some other plot like EC, EF, and EFP, the carrier density. Okay, you can plot the carrier density at the VD equal to 10 volt, VG equal to -3 volt. Okay, so you can look at this. All right, so this is a 2DEG in the channel. Okay, and you can find that the 2DEG here is like a 4E5, and there's a heavily doped region, so carrier density here is high. So this is like ohmic region, and current flow in this direction, and this is a 2DEG. So you can also check about what is temperature, because we consider about the temperature. So you can plot the temperature profile, and this is the channel's temperature profile, and the highest temperature, as you can find, is around here. So you can check that in the channel layer, there's a large heating area just around the gate corner. Okay, you can find this. All right. So this is the node-based data, and the element-based data. You can also plot the 2D plot of the absolute value of E. Okay, and E or E, maybe that's the problem. Okay, anyway, we can plot the electric field profile and the loss scale. So we put the loss scale and the upper bound. Okay, 7E minus 7 and the 5E5. Okay, so let's look at the electric field. The electric field, we can also plot the 2D, and we can check about where is the high field region that causes the breakdown. Okay, so in this plot, you can find that the large electric field is in the corner of the contact region here. Okay, so if there's a leakage current, this will be some breakdown region. However, if you look back along the channel, you can find that there's also a peak electric field here. This is along the channel, because channel has current flow, so sometimes breakdown will be along the channel. Okay, so this is a ESEY, and let me see anything we can plot. Okay, we can plot the trap density. Yeah, it's more that there's most effective trap. Okay, so we can plot the trap density when we apply the bias. Okay, this is the trapping density, and there's only a two region we have a trap. One is the buffer, we have electron trap. Find here. Okay, and let's plot the loss scale. Let's say YE19 and 4E15. Okay, if we look at loss scale, maybe we can see something different more clearly here. There's a negative region. Okay, so you can find that there's a trap in here, and any service trap. Okay, the service trap is here. Only trap in the junction, and there is no service trap along the silicon nitride column region. So they were depleted. Okay, and in the contact region, there's a large density of service trap here. All right, so this is the trap, effect of trap, and then we can see anything else we can find. Element check, no data. Okay. All right. So then we go back to IV. If we plot at this, we know the IV, so we can plot the VG, and the X value is VG, and the Y value is source current or drain current. So we can find a -4 volt minus, this is the current density. Okay, so it's not closed, and we calculate 3-point. All right. So this is the profile here, and actually we ran a set, because if you want to run the IDVD curve, it will take some times. So for example, if I start here, and you can run multiple in parallel. So I can run a multi-bias range. For example, I can run VD for multicast. So or run VG for multicast. For example, if I want to plot IDVD curve, I can plot for 0 and this is 1.0, and the VG start at 0 and 10. And I say this is 0.5. Okay. So we can use this, or we can run a multi-parameter region, and of course that we can set up VD equal to 0 and 0, and this is 0.5 and -4, -4. And let's start to run. Set up, save as a new project, and we can say another demonstration project and -2. Okay. So you will start to run. So the first project you will run is VG start from VD from, okay, sure. This is VG equal to -4 vs 0. Okay, so this is the first test. Okay, so then we can test start. We can run the multi-test. Okay, run VD for multi-test. Okay, yes. Okay, save. Then you will run a multi-test. It take a little bit time. So just don't save as a new file, but because I want to change the name, so I save a new file. Then I need to rerun the multi-test again. So, all right. So as you can find, it runs several jobs in parallel. So if you have many CPU, okay, you can run this. Okay, you can find VG -3, VG -4, and this is VG -2, and VG -1. And this original project is this. This will be overlap a little bit to this. Okay, so that's the issue. But otherwise, it will run several BIOS case. Okay, so this is for running multi-test. After finish this, you can run a IDVD test. You can take a rest, going home, and take a coffee break, and then you can come back to check the data. All right. So let's demonstrate some data we calculate from this case. So we open the previous testing case. So this is the testing case we have run. So the IDVD curve we have so far test. Okay, is something like this. You can plot the IV, and IV can start from IV curve. So we can plot JS source current to VB. Okay, so you can find this is a IDVD curve, and this is VG0, -1, -2, -3, -4. So this is IDVD curve. And for the transverse curve, I plot here, Y is VG, this should be VG, and we can plot the transverse curve. So this is the -4 volt to 0. This is the ID VG curve. So in the program, there's a sign issue is that if you plot the JD, then you will find it's negative. That's because current is flowing out the GaN contact, so it will be negative in our definition. And if current is flowing in the GaN, it will be positive. So there's a sign issue, but this is fine. You can simply just neglect this. Okay. So usually you can just plot the JS because JS is a current flow-through. But when JS is not equal to JD, then you need to plot them separately. So you simply negative by a sign arrow. And all the raw data is here. So if you want to plot by your plotting tool, you can simply copy the VG, VD, VS, JG, JS, JD into your Excel and plot your data. So you can also plot, there are many information that you can plot, like the maximum temperature. So you can find the temperature change with bias from 300K to 500K. Okay, you can find that's the difference of the temperature, also the average temperature. Average temperature is the average region in the channel region. So you can also plot the average temperature. And you also have many information that you can plot. Okay. Then the most important is check the error to see if the convergence is good or bad. So you can find that the converge the VG close to 0 is not good. It's not good. Okay. So there's some convergence issues here. And also you can find in this case, there's a convergence issue also. Typically is around VG, when VG is small, like 0 volt, the error is large, but good convergence here. Okay, so running this case will take some time, and the convergence will also make the simulation took a long time to get converged. So this is the case we can demo, and that's all.